Hi, welcome to this tutorial on continuous random variables. Now in this tutorial I'm going to introduce you to probability density functions, often called PDFs. And the best way I can think of doing that is by starting off with a grouped frequency table as I have here. In this column I've got the time in minutes x taken to do a particular task by a number of students. Now the frequency f, the number of students that took more than or equal to 1 minute but less than 2 minutes, was 20. And 50 students took more than or equal to 2 minutes but less than 3 minutes to do the task, and so on. Now suppose I wanted to work out the probability of taking between 1 and 2 minutes, for instance. How would I work that out? Well, I could work it out from this observed data here. I could total the frequency, which comes to 100. So we've got 100 students. And so if I was working out the probability, or some people call it relative frequency, I would need to do the frequency divided by the total frequency. So for the interval 1 to 2, we have 20 students out of 100 who took between 1 to 2 minutes to do the task. So 20 divided by 100 is 0.2. Similarly, I could look at the 50 and do 50 divided by 100, and that's 0.5, and for the 30 that would be 0.3. So these would be the probabilities. Because we're looking at everything, you'll notice that the probabilities total 1. So we'll just mark that in as the sum of those probabilities is 1. Now suppose I wanted to carry on and work out what we call relative frequency density. Now what is relative frequency density? It's defined by f of x, where f of x is the relative frequency, or the probability, divided by the class width. So for this particular row we have the relative frequency being 0.2, and if we divide it by the class width, which is the gap between 1 and 2, which is 1, then we've got 0.2 divided by 1, which is 0.2. Similarly, for the 0.5, we've got 0.5 divided by the width here of 1, so that's going to be 0.5, and for the other value, that would be 0.3. Now, suppose we drew a graph of the relative frequency density f of x against the time in minutes x. Then we would get a histogram, something like this. We would have the 0.2 as being the relative frequency density over that interval 1 to 2, and similarly 0.5 over the interval 2 to 3, and 0.3 over the interval 3 to 4 minutes. Alright, so we've got a histogram like that. What I'd like to draw your attention to is also notice that the area of any bar represents the probability. Take this first bar for instance. F of x is 0.2 as we've got up here, multiplied by the width 1. 0.2 times 1 gives the probability of 0.2, and it's the same for, as I say, all the bars. Okay, let's move on. Now it's all very well that I've got 20 students who took between 1 to 2 minutes. But suppose I divided this interval and all the other intervals up into finer divisions. Let's suppose we split them up into half units, something like this. So for the first one we have got x going from 1 minute to 1.5 minutes, and then from 1.5 to 2 minutes. And if I did the same for the other two classes, we'd have 2 to 2.5, 2.5 to 3, 3 to 3.5, and then we would have 3.5 to 4. Okay, now we knew that there were 20 students who took between 1 and 2 minutes, but if we break it down to these class intervals, how is that 20 spread over these intervals? Well, maybe it was 5 and 15. And for this interval between 2 and 3 we had 50 students taking between 2 and 3 minutes. But if we split them up into these two intervals, maybe it was 20 and 30. And for the last class interval, for the 30 students, maybe it was 20 and 10. So if we work out the probabilities, or relative frequencies I should say, then for the value 5 we would be doing 5 divided by 100, 5 out of 100, which is 0.05. And for the 15, that would be 15 out of 100, 0.15, and so on for all the other probabilities. And if you add these probabilities together, you should find, again, you get 1. Now, what I could now go on to do is work out what the relative frequency density is, f of x, for each of these values that I have got in green here. Each of these probabilities, if you like. And remember that to work them out, what we need to do is take the relative frequency and divide it by the class width. Now, each of these class widths is 0.5. So if I take this value, 0.05, and divide it by the class width, 0.5, what I get is 0.1. And if I do the same for all the other values, I get these values here. And what I could do now is draw on a histogram again for the relative frequency density f of x. So for the first one, 0.1, that's going to be a bar at a height of 0.1 over the class width 1 to 1.5. And if I draw that on, you'll see it's going to look something like this, shown in green. What you should notice is that the bars are obviously more densely packed than the blue bars. Nothing changes as far as the area of a bar represents probability. Again, if we look at this first bar, for instance, we've got the height is 0.1, that's f of x is 0.1, this value here. And if we multiply 0.1 by the class width of 0.5, you get 0.05, the probability. So, again then we have this idea that the area of any bar represents the probability. Now suppose we subdivide all these intervals again and go on to draw the relative frequency density histogram. Maybe it would look something like the one I've just drawn here. And imagine keep dividing all these intervals up till we get very, very small widths. Each width eventually becomes infinitesimally small. Now the tops of the bars would smooth out to give a curve, something like this. And outside of these bars we would have no probability. Alright, f of x would be 0. Now in general, what we have got is this. F of x, we would plot the curve, and this curve and the parts outside of it are called a PDF, or probability density function. And what we should know is that the area always represents probability. And we should know that the area under a graph is given by, or calculated by, integrating the function of x. So in other words, the area under the graph f of x dx going from the lowest limit, which we'll say is minus infinity, all the way up to infinity, all of that area should total 1. It's basically the sum of all the probabilities, and that will come to 1. And if we want to work out the probability of being between two values, say A and B, that is given by this area in here. And so to work out that probability of our random variable x being between A and B, that is going to be given by that area, and the area under graph is given by the integral of f of x with respect to x going from A to B. So we've got these two facts, and there's one more fact about a probability density graph. The function f of x is always going to be greater than or equal to 0. So for the third fact, we need to say that f of x is greater than or equal to 0 for all x. So we have three facts which you should try and remember. Okay? And in my next tutorial, what I'm going to do is show you how we use each of these particular points to do probabilities on a continuous random variable.